Welcome back to the class Computational Neuroscience, Neuronal Dynamics of Cognition. This video presents a mathematical detour and should be interesting for those who want to learn more about the relation between STDP and rate-based Heppian models. Those not interested in the math can go straight to part 7. So now let's redo the same kind of argument, but from a more mathematical perspective. So I assume that the input is given by Poisson spike trains. I assume that the output is also given by a Poisson spike train. So the probability that it will find a spike in a very small time window of length delta t is the rate times the delta t. This is the probability of firing in this interval delta t. Now we are interested in the weight change over a much longer time window, which I call capital T. So we consider the weight change in this interval, and this is the sum over all spikes of the presynaptic neuron, of the postsynaptic neuron that occur in this window, capital T. Let's first rewrite this expression. And to do that, I use this notion of a spike train. I have here my spikes. The spikes sit at some time, which I call Ti f prime. So this would be f prime equal 1, first spike, second spike, third spike. So the spike train is the sum over all these pulses, T minus Ti f prime, sum over f prime. Similarly, for the presynaptic spike train, I can write it as Sj of t, sum over all the pulses, sum over f delta of t minus tjf. And I will use this expression now to rewrite this expression sum over all pairs of spikes. So let's first keep the postsynaptic spike fixed and consider the presynaptic spikes. I can rewrite this by saying this is w of t minus ti f prime integral s of t dt integral from 0 to t, and I kept the postsynaptic spikes, so I still have to sum over f prime. Now these are delta functions, so if you plug this back in, you see that you get back to this formula. You take the red term here with these delta functions, you insert it here, you find this back. I can do something very similar for the postsynaptic spike train. I insert this as well. So let me write this as w of t minus t prime, s of t, s of t prime. And now I'm missing the indices. So here I had replaced the presynaptic spike train. So this is Sj of t. Here I had replaced the postsynaptic spike train. And here I integrated from 0 to t. And here I integrate also from 0 to t. And this goes over dt prime. Now let's look at the timing difference. So this is a small s time difference between pre and postsynaptic spike. Let's introduce this here. So I have a weight change, which I can now write, taking this formula here, w of s. And I will keep this term here. I have si of t prime, and if I have t minus t prime equal s, then I can write t as s plus t prime, which means this sj gives s, and the integral now goes over s. So I have here the integral from 0 to t, but I assume that t is very large. So it doesn't really matter whether for one of the integrals, I put the bounds to infinity. So I will take the integral over s from minus infinity to plus infinity, and then I keep the integral over dt prime, and this is my change w from 0 to t. Final steps. I rename t prime as t, and I write a 1 over t in front here. Why is this interesting to have a 1 over t? Because I have here still the integral over my interval. If I'm interested in the mean change per unit of time, I should divide by 1 over t. And this gives my final formula. The rate change, delta wij, over capital T, is the integral over the learning window. And here I have the two different spike trains. So far, this was an exercise in rewriting. Now we come to the real Poisson model. What are our assumptions? We assume that the presynaptic spikes are generated by a Poisson process. So spikes are independently generated with a certain rate, the presynaptic rate ν(j). Similarly, I assume that the postsynaptic spikes are generated independently and with a rate ν_post. And this rate, similarly, the presynaptic rate is constant in time. So the presynaptic rates are generated by a Poisson process. That's my assumption. The postsynaptic spikes are generated by a Poisson process with also fixed rate, and this fixed rate is independent of presynaptic spikes. Now this is a strange assumption. I will loosen it later, but for the moment just keep this. And then I ask, what's the expected change of weights, delta wij, over a time window t? In expected means I take the expectation signs. So that's the program. Now we had on the previous slide the result that the weight change is this. So we now assume that all the firings are independent Poisson process and we take the averages. So let's look at the averaging. This is the averages. The averages go over the whole interval, but this is a fixed deterministic window, so the real averaging is just over the spike trains. And now you see that what matters are the correlations between presynaptic spikes and postsynaptic spikes. However, I have assumed that presynaptic spikes and postsynaptic spikes are independent. So this is Si of t, this is Sj of t plus s, ds dt, w of s minus infinity to plus infinity 0 to t 1 over t. Moreover, I assumed that these are fixed rates, constant rate. So this is the rate ν(i), the postsynaptic rate. This is the rate ν(j). All the time dependence has gone, so I can take the integral directly over w of s ds from minus infinity to plus infinity, and then I have another integral from 0 to t over something that's constant in time, so this just cancels out, which means my weight change, delta wij over t, expected, is presynaptic rate, postsynaptic rate times the integral over the learning window. Thus, we made the transition from a STDP model to a rate-based model, and what we found is that under the assumption of independent Poisson processes, we get a term that corresponds to the correlation term with a prefactor, A2 core, which is equal to the integral over the learning window. Now, there's something very strange here, because we started off with a Heppian idea saying that, well, the presynaptic spike that contribute to firing the postsynaptic ones are the important ones to change the weight. So there's this causal interaction. If a presynaptic spike arrives, it actually causes a change in the neuron. So it's very strange to assume that I have independent Poisson processes. And therefore, in the next part, I will look at a model where presynaptic spikes cause EPSPs, postsynaptic potentials, so that there is no longer an assumption of independence between pre- and postsynaptic firing. Before we start with the model that includes EPSPs, let's change our writing styles. I already explained that we can make the transition from a notation sum over all pairs to a notation where I have spike trains, postsynaptic spike train and presynaptic spike train. I just mentioned that in Happy and Learning, the causal relations between pre- and postsynaptic spikes are important. So let's look at this again. I have my learning window centered at the postsynaptic spike. It has a positive part and it has a negative part. Now, if we assume that one of these presynaptic spikes, this one here, arrives just before the postsynaptic spike, then I can think of this postsynaptic spike as the one that triggers the change. If pre before post, then the change delta W is, in this kind of formula, is triggered at the moment of the postsynaptic spike. And so this, I can pull this out and say the changes happen at the moment of the postsynaptic spike under the condition that the presynaptic spike is before the postsynaptic one. But it's before the postsynaptic one if S prime is smaller than 0. So this part here is S prime smaller than 0. Or I have a notation where I say T minus S, where S prime is minus S. So this part here has all the conditions pre, before, post. Similarly, I might consider a situation where I have a presynaptic spike here and I had a postsynaptic spike just before. Then I consider that this spike here, this presynaptic spike, causes the weight change. So I pull out this term for the condition that S prime is larger than 0. Now the postsynaptic spike occurred first, and then I have a term that says the update happens at the moment of the presynaptic spike. So why did I discuss this? Because you see that there are terms that really consider the situations pre, before, post. And this is the situation where presynaptic spike could have participated in triggering the postsynaptic spike. And this is what we are going to formalize next. So here I have my presynaptic spikes and I have postsynaptic spikes. The difference now is that I say each presynaptic spike causes an EPSP. So let me explain this. I have my presynaptic spikes at time TJF. For example, there's a presynaptic spike here. It causes an EPSP, which I call epsilon of T minus TJF. This was the first spike. Then I will have other spikes. And basically this formula says I just add up the contributions of the different presynaptic spikes. Now the firing rate of the postsynaptic neuron is now time dependent. The firing rate goes up, goes down, goes up again, goes up, and so forth. To rewrite the postsynaptic firing rate, I use the presynaptic spike train. I write epsilon of S as J of T minus S ds, sum over J Wij, where the presynaptic spike train is the sum over all presynaptic spikes, delta of T minus TJF. So if you plug the definition of the spike train back in, you get to this formula that I had before. We will be interested in the expectation. So this new post, this is this firing rate, this time-dependent firing rate for this one very specific realization of the input spikes. But now we can ask, well, what should we expect? What happens on average? So now I look at the expected postsynaptic rate. Well, where does the expectation sign go? Let's do this here. I have my expectation. This is a fixed weight. This is a fixed time course of the EPSP. The only stochastic part is the realization of this spike train. That's one of the realizations. There are many others. Now the expectation of this is just the firing rate. This would be the presynaptic firing rate. And I still assume that the presynaptic firing rate is constant. Now since it's constant, I can take out the integral and I have sum over j wij integral epsilon of s ds. So the expected rate is constant and proportional to the presynaptic firing rate. So that means in expectation, this is my postsynaptic rate. So in expectation, I don't see anything of these causal effects that each presynaptic spike causes a postsynaptic spike. So over many different realizations, sometimes the spike train is like this. Sometimes the spike train is like this. And over all these different realizations, this is what I expect to see. Now, where is the causality? Let's change the perspective. Say, I know, so on average, the spikes come wherever they come. But I know for sure that there was one spike here. So there was one presynaptic spike here. Then on average, I will have this trace here. But since I know that I have this extra spike, that actually means I know for sure that this extra spike causes an EPSP. And this EPSP changes the firing rate by an amount wij epsilon of t minus t prime, where this is the presynaptic spike of my neuron J. So if I look at the expectation nu I post of t given the specific spike that I know for sure that has arrived at time TJF, and look at the expansion of this, then I see my normal trace, which I can copy from above, wij epsilon of s ds times nu j pre, and then I have this extra bump, so I write plus wij epsilon of t minus tj prime, tj prime. So I should change this here. What I meant is this specific spike at time tj prime. So we have to distinguish between the normal expectation, where I just say, I don't know what happened, so spikes arrive whenever they want, and the expectation given an input spike at time tj prime. And this extra spike makes a causal contribution to the postsynaptic firing rate. Since this is the same term, I can also write this in the form, this is the normal expectation plus the extra term wij epsilon of t minus tj prime. And this is now what we are going to use on the next slide. So 2 slides ago, I've already introduced the different notation styles. This notation style says for minus s, this is the condition before post. This is where the causal effects can take place. This is the condition of post before pre. If the postsynaptic spike comes before the presynaptic ones, then there cannot be any causal relation anyway. Now we are interested in the expected weight change. So let's take the expectation signs. This is the fixed positive part of the learning window. The expectation goes to this. This is the fixed negative part of the learning window. The expectation goes to the spike trains. Now, since this is post before pre, there cannot be any additional causal information. So this part is similar to what we had seen before. It's just Sj of t averaged times Si of t minus S averaged. The interesting part happens over here. I have a part that just says, well, there's a contribution of nu I pre times nu post each time expectation. This is where I split it up. The same way I would do it here. I would say this is nu j pre nu I post. And so I see that the indices are not correct. Post is I, j is pre. But I had here the extra green part that says, but look, for any extra spike, I have this term wij epsilon of the firing times. And I have to treat this extra term together with the learning window. So I will have here the normal term. If this is constant, I just close the learning window. V of minus S from 0 to infinity times post. And then I have the extra part that says, okay, I have here W of minus S, I have epsilon of S, ds. But this term was for one single spike, one single given presynaptic spike. I will have more spikes on the presynaptic side if the firing rate is higher. So I have to multiply here in addition with a nu j pre. So let me sum up. From the green part, I have a term wij integral w of minus s epsilon of s times nu j pre. And then from the other parts, I have the integral over the positive part of the learning window with minus s. I have the integral over negative part of the learning window with plus s. So this goes back to a full integral from minus infinity to plus infinity double of s ds times nu j times nu post. So this is my total expected weight change. ddt wij expected is this term here and this term here. Now this looks like a rate model. So let's compare this. In my general rate model, I have terms of this form. What we found is that this factor is the integral over the learning window w of s ds. So this term is A2 core. And then we found an extra term that was proportional to the spike arrival rate, which means that this A1 pre is my extra term, which is w of minus s epsilon of s ds. Then we did not find this term and we did not find this term. So I have two terms. ddt wij in the expectation is this term times nu j pre plus this term nu j pre nu I post. So this causal effect is proportional to this weight here. Let me interpret those terms. So this term here, A2 core, is the integral over the learning window. Positive parts minus negative parts. This term here works like this. You plot the learning window, and what matters is the minus side. So this is S, this is the negative side. And then you compare this with epsilon. So if I take this and I plot this back as minus S, then this is like flipping the learning window around. So flip this around and you have this contribution. So this is W of minus S. And then we have also the EPSP, which looks like this. So what matters here for this term is the similarity between the EPSP and the flipped over learning window. The positive part of the learning window, but flipped over to the other side. So let me summarize this. Yes, for Poisson input, STDP models are indeed related to rate models. And I find two terms. I find a term that is proportional to the presynaptic rate. And for this term, what matters is the similarity between the EPSP and the LTP part of the learning window. And then I have another term, which is nu pre times nu post. And what matters for this term is the integral of the learning window. Now for the mathematical parts, I used expectations, delta notation for the spike trains, correlations of Poisson spike trains, and there's additional information on this on a separate video.